So the first little bit of this particular chapter is just going over the radicals and finding the square root and the cube root of things. And this is a part review because you've seen this before in Algebra 1. You know the square root of 4 and 81. Those are pretty straightforward. But the first thing I need you to do is to actually write down some key vocabulary that I'm going to keep using throughout this whole thing. So the first thing I need you to write is really important because of the fact that it's actually going to be on your quiz. It's going to have a bunch of different blanks. You're going to have to fill in the correct vocabulary word. The only thing I'm really going to give you is the square root symbol or the radical symbol. So next to this, we'll say this is our radical symbol. Make sure you have both words. And then underneath the radical symbol, we have any sort of numbers or variables, and those are called our radicand. In front on the little leg, if you will, is something called our index, and this will be represented by a number, or sometimes it'll be blank. But if you look beneath on the types of radicals right down here, then you can see that we have a couple of square roots and cube roots and fourth roots. And if you look closely, they actually have different indexes. So here we have an index, here we have an index, and there. When it comes to a cube root or fourth root, it's pretty obvious what our index is. It'll be 3 or 4 or 5. But the last one, really the first one, that square root doesn't have any number in front. But if we think about a square, that is going back to our Algebra 1 days, we can think about it as 4 squared or maybe 5 squared. Then we understand that the understood index here is actually 2. So the last thing I need you to write on the definition portion is the space in front, which I am going to annotate with a box so that you know it's in front of our radical symbol, is going to be our coefficient. And again, this is back to our Algebra 1 days. If you had something like 4x squared, that 4 in front of your variable is your coefficient, Okay, so let's do some examples. When we're doing the smaller numbers, it's pretty easy. Number 1, 4 squared is 2, 121 is 11, square root of 81 is 9, and the square root of 36 is 6. So those are not difficult. We know those. The question comes to, well, what if we have a bigger number like 256? Like, what do we do? Well, the easiest thing to do is to go ahead and write out all of your squares. So I have things like 1 squared, which is 1, or 2 squared, which is 4, and I can keep going on and on. The most common ones are going to be 1 through 12. So it's a good idea to have these written down somewhere, or make sure you are extra sure that you know all of these. So let me just finish this up. 10 squared is 100, 11 squared is 121, and then 12 squared is 144. So what I'm going to do is I'm going to take 256 inside my calculator, and I'm going to start dividing them by my perfect squares. Now, perfect squares are this portion right here. These numbers, if I were to put them underneath a radical, underneath the square root specifically, they would be a perfect number. I wouldn't get a decimal. I would get a sure whole number. So I'm going to start with my smallest number I can think of, which is technically 1, but 1 is just going to give us 256 again, and that doesn't really help me. So I'm going to start with 4. I'm going to divide 256 by 4. And if I get a decimal, then I know 4 does not work, and I need to move on to the next number, which would be 9. But I'm going to take 256 divided by 4, and it actually does give me a whole number. So I'm going to rewrite it by what I divided with, which was 4, and what I got, which was 64. So another way to think about this is 4 times 64 is 256. Now, the cool thing about these two numbers, which I'll show you right here, about these two numbers is that 4 is a perfect square, and so is 64. So that works out for me because I'm going to take the square root of 4 and get 2, and take the square root of 64 and get 8. And since they were multiplying underneath the radical, they can technically be multiplying outside of the radical. So 2 times 8 equals 16. And this becomes my answer. So if I wanted to double check, I could take a calculator and I could say, okay, 16 squared equals what? Well, it equals 256, which is exactly what I started with right here. So I know that I did this correctly. And I'll do the same idea with number 6. I have 484. I'm going to take 484, put it in my calculator. I'm going to start by dividing it by 4. It should work out. And it does. I don't have a decimal, so I'm good with that. So I'll rewrite it as 4 times what I got, which was 121. The square root of 4 is 2. The square root of 121 is 11. So 2 times 11 is 22. And that's my answer. Again, double check your work. 22 squared is, in fact, 484. So then the next section on that first page of the worksheet that we have follows the same idea, but now we're working with a cube root. And so before we get started, I'm going to go ahead and list the first 9 perfect cubes. Let me erase all this first so that I can have room. But I have 1 cubed, which is 1, 2 cubed, which is 8. And remember, I'm getting all this by just going to my calculator, and cubed just means that I do it 3 times. So like 6 cubed would be 6 times 6 times 6. And so I'm just writing these out. You can go all the way to 12 if you would like, but I only felt the need to go up to 9. And so now that I have this, it's a lot easier for me to answer some of these questions. Number 13, I already wrote what the answer is. The cube root of 8 is going to be 2. Underneath that, I actually have a negative, which is something we've never seen before. You can have a negative underneath a square root, but I will tell you that it follows different rules. So we will get to that in chapter 3. But it is possible to have a negative radicand for odd-numbered indexes or indices, or I don't know how you pluralize that. But either way, so if I were to take my calculator and find the cube root of -1, it would actually tell me that my answer is -1. So -1 times -1 is +1. +1 times a third -1 is -1 again. So it does work out. So that's my answer. 14 would be -5. Again, I have it in my list already. I'm going to skip number 17 for a second and move on to 15 and 18. 729, I've already mentioned, it's going to be a +9. And number 18 is the cube root of -343. So my answer will be -7. All right, so number 17, this is a really big number and it's not in my list, but I'm going to do the same process as I did before. I'm going to say, all right, 4096, I can rewrite that as, I'm going to take that in my calculator and divide it by 8. Remember, we technically can start with a 1, but that doesn't really give us any other information. So we just go to the next number, which is 8. If that doesn't work, we would move on to 27. But if you divide by 8, it actually equals 512. So we did actually get 2 perfect cubes, not perfect squares anymore, but perfect cubes. So this is the perfect cube, and then so is the 512 over here as 8. So I'm going to take the cube root of each one, and the cube root of 8 is 2. Cube root of 512 is 8. And so 2 times 8 gives me 16. So if I type that in my calculator, 16 times 16 times 16, I do in fact get 4,096. So the question is, what happens if you don't have perfect squares or perfect cubes? What do you do? So really, again, it's using some principles and some concepts that we've actually already learned from Algebra 1. But what we're going to do is, instead of using our perfect cubes and stuff to do stuff, we're actually going to create a factor tree. Now, personally, I don't really like factor trees. I think they're a little messy and it's easy to miss numbers. So I teach something called the birthday cake method. And it doesn't matter to me if you choose to do this method or if you're comfortable doing the factor tree to stay with the factor tree. I'm fine with that. I don't really care. But basically, all we're going to do is we're going to get the factors of all of our radicands. So in the first little sections, 1 through 6, I'm only going to do the first 3. I'm going to take my radicand, 24, and I'm going to find the factor of that. Now remember, when you're doing this, you only want prime numbers. So numbers like 2, 3, 5, 7, 11. Once you are again, when you're dividing by a prime number, if it gives you a decimal, that means it will not work. So you should go to the next one. So if we were to divide this by 2 and get a decimal, I would then go to 3. If I got a decimal again, I would go to 5. Again, I would go to 7. Okay, so you start at the bottom and you work your way up. So if you try the first 3 and you're like, I'm still not finding it, you just got to keep going to the next prime number. So I'm going to divide by 2. It does, in fact, give me 12, so I'm going to put this right here. And if you notice, the radicand is like the base of my cake, and I'll show you how it's a cake in a second. For those of you who have come from Algebra 1 here at our school, you might realize that this is very similar to upside down division, but it's just going upwards like a cake. Anyway, so I get 12. I can divide that again by 2 to get 6, and again to get 3, and divide that to get 1. The 1 on top is a birthday cake candle. Okay, so that's why it's called the birthday cake method. Again, if you are better with the factor tree or upside down division, then go right ahead and do that. I don't really care. Now, the thing is, in order to leave the radical, I need to have 2 of the same number, and I know I need 2 of the same number because remember, our index right now is not there. And so if it's not there, it's an understood 2. That's what we mentioned before. So I need a group of 2 in this case to leave. So I see that I do in fact have a group of 2 right here, and they happen to be the number 2. So they're going to get to leave. And then the 2 pieces that are not circled, because they do not have a matching pair, are going to stay under the radical, and they're going to multiply because they're factors. Factors are multiplication. So my final answer is going to be, after I simplify this, it'll be 2 times the square root of 6. And I just keep doing that over and over again. So number 2, same idea. I'm going to take my radicand. It's going to be the base of my cake. Divide by my first prime number. It works, so I keep going. Divide by 2 again to get 12, again to get 6, again to get 3. And remember, go one more time so that you can get 1 on top because that is your birthday cake. All right, I have a group of 2 here, and I have a group of 2 here. So now both groups get to leave. Notice when both groups get to leave, it's not 2 times 2 times 2 times 2. It is, they become the same number. So the first group is going to leave and become 2. And then the second group is going to leave and become their own 2. They are coming together. If you think about it, 2 times 2 is 4, and the square root of 4 is 2. So that's why instead of having 4 or 4 2's, we end up with just 2 2's. Anyway, the only piece that's not circled is that 3 right there, so it stays underneath the radical. And again, our final answer is when we simplify this. 2 times 2 is 4 times the square root of 3. We'll do it one more time. 72, our base, that's going to give me 2. 36, I can divide that by 2 again. That gives me 18. I can also divide this by 2, so I'm just going to keep going. I get 9. Now I have to change. 2 does not work. It gives me 4.5. Decimals are not okay. So I'm going to divide by my next prime number, which is 3. Divide that 3 by 3 again so I can get a 1 because that's my birthday cake candle. Okay. So again, we're looking for pairs or groups of 2 of the same number to leave the radical. I have the 3's up top and the 2's on the bottom. If you had wanted to maybe pick these 2's instead, that's fine. It doesn't really matter. It's totally arbitrary of, the 2's. As long as you have 2 of the same number, I'm happy. So the 2 of the 2's get to leave and the 2 3's get to leave. So it's going to say 2 times 3 from each group. And then the piece that is not circled stays underneath the radical, which is 2. So 2 times 3 is 6 times the square root of 2. And that is our final answer. So then the next part, notice how instead of working with the square root, we're now working with the cube root, which means now in order to leave the radical, I need to have 3 in a group of the same number in order to leave. So I'm going to do the same process all over again. I'm going to take 40, my radicand. It's going to be the base of my cake. I'm going to divide by my prime numbers. 40 divided by 2 is 20. 20 divided by 2 is 10. 10 divided by 2 is 5. Divide that by 5 one more time to get our birthday cake candle. Okay, now I can see I have 3 of the same number. I have actually 3 2's. So I'm going to circle that. It gets to leave the radical, and now the piece that is not circled, the 5, is going to stay under the radical symbol. Now remember, we are now working with cube roots, so I'm not going to write 2 times the square root of 5. I'm going to say 2 times the cube root of 5, and that is my answer. Same process again for 500. 500 is the base, divide by 5 to get 100, divide by 5 again to get 20, divide by 5 to get 4. And then from here, 2 times 2 is 4, so we know that. This is our birthday cake candle. It's beautiful. I always want to sing happy birthday when I do this. Anyway, I have a group of 5. I do have 2 2s, but unfortunately I'm working in the cube root system, so I need 3 of the same number. So the 5s get to leave, and the 2s stay, and I have 2 of them, so they multiply. And remember, it's cube root, so this is going to equal 5 times the cube root of 4, and that's my answer. 162, last one. This we can divide by 2 to get 81. 2 does not work whenever we do this, so we're going to divide by 3 to get 27, divide by 3 again to get 9, and then easily we know 9 is 3 times 3. So here's our 1. And I have a group of 3 right here at the top. Again, you could have picked, the 3 above the 2. I think that's fine. It doesn't really matter. As long as you have 3. You can't have 4 in a group. You can't have 5. You have to have 3. Only 3. Even though there's a 4th 3 right there, that's sort of like, hey, what about me? Don't care. You can only have 3 in a group to leave. So the group of 3 gets to leave. It's still under the cube root, and it's 3 times 2, which is 6. So this is our simplifying the perfect roots and the non-perfect roots.